Okay, let's start. Do you have any questions? All right. So far, right, what we're discussing is still around Brownian motions and its properties. Okay. So again, let's review the definition of Brownian motion. So WT is a Brownian motion if it starts at 0, it has stationary increments, and finally, right, it has independent increments. Okay. So now, last time, right, we were discussing some kind of expectations, right? Expectations, conditional expectations. And, what else do we discuss? The moment generating function. Okay. It really is about the normal, right? About the normal distribution, about this aspect. And of course, conditional expectation, right, talks about that aspect of, let's say, normal, right? Mu sigma square. And of course, that, by itself extends to Brownian motion. We also mentioned so now in terms of the calculus aspect, right, of the Brownian motion, we mentioned the fact that the Brownian motion path, right, WT, is nowhere differentiable. So you cannot find a point, you cannot find any t, okay? And what it says is that it's so amazing that if you just look at a path, a typical path of the Brownian motion, starts 0, right? It does whatever it does. So my drawing here does not even capture, right, what happens in reality. What basically it says is any point that I pick, right, any point t, if you zoom in, it will look like a corner, right? Every point, so there's no straight line like this in reality, okay? If you pick a point and you zoom in for a Brownian motion path, you see a small corner, okay, anywhere. So, and that, of course, if you think about it, extends to the stock as well, because the stock price is exactly a function of the Brownian motion. So it cannot, okay, be differentiable either, which basically roughly explains why, right, stock trading cannot be predicted, okay, at least from this point of view, because from any point, you cannot draw a tangent line that predicts, at least for the next second or so, the movement of the stock price, right? If you have observed a stock market, a particular stock price, pick any second in time and ask yourself, if the stock is going to go up or down in the next second, chances are you will only get like 50% correct, right? Because there's no prediction there. There's no pattern, okay? All right, so this kind of, it leads to the next question, which is the stochastic integration question. Which has to do with the value of a portfolio, okay? So if we have a portfolio, pi, okay, consisting of the stock only, right, that holds, delta t shares of S at time t, okay? Then if somehow you assume that you start out with $0. Okay. Of course, this is kind of a bit, so this is a bit strange because you start out with $0, you cannot buy stocks to begin with. But like, so there should be a cash account on the side that allows you to borrow and cash or save cash kind of thing. Here we don't want to go to the the precise financial description, so we'll skip that. But we'll go back, okay, when we really want to discuss portfolio proper. Here, all I want to say is that, you know what? Yeah, no, let's do it. If I want, I can do this too. Let's say you start out with some cash, let's say C, okay? Then the value of portfolio times T will be the original cash plus the change that has happened during the time interval 0 to T. So right here, right, this quantity describes the portfolio value change, right? Portfolio net change on 0 to T. And why is that? Okay, remember this D notation, right? This differential notation is nothing but a, well, okay, it has this precise meaning, but approximately what it describes is a small change, is the change, okay? It's a change in the stock price, right, as time moves a little bit. So if you multiply the shares you hold with the movement in the stock price and add them up together, right, you get the portfolio net change. All right. So that's a financial angle behind the mathematics that we're looking at. But basically, if you remember, right, so here, the Black-Scholes model, one second. Sorry. The Black-Scholes model says that, okay, a change, right, in the stock will be the rate return times the current stock price in time. Okay, that's like the deterministic return. Like this is like your saving account. Okay, or like the usual growth plus a stochastic growth, which is volatility driven by Brownian motion. Okay, so this is your deterministic growth. Or if you want, right, average growth. So when you hear something like, the stock has a return of, let's say, 7% a year, let's say for Microsoft or something, they're referring to mu, okay? And the unit of time is a year. So 7% a year is this, okay? But of course, right, that doesn't mean that if you hold Microsoft stock for a year, then you get exactly 7% at the end of the year, right? Sometimes you get 3%, sometimes you get minus 5%, sometimes you get 12%, right? The whole point is if you average out over, like, let's say 30 years of investment into Microsoft, then each year you see is roughly 7%. So exactly, right, that mu is the one that is contributing to that 7%. But of course, right, the variation in each year comes from exactly the Brownian motion aspect, all right? So this is the, I don't know, stochastic return, if you will, or, just a component that exactly explains the fluctuation in the stock price, okay? And I'll just call it return, but basically, is the part that will amplify, right, or add noise to the trend of the growth of the company. Anyway, point is, if we plug this structure into the portfolio, what we get is the original cash that we have, or the original value of the investment, and then however much you hold times the deterministic return, and then however much you hold times the stochastic return. Okay. And again, this part is easy to understand. And if you do any like differential equation class, you will study this kind of first order differential equation, all right, and see how you solve for it. But when people invest in a stock or anything, or asset, that's what they have in mind. But of course, right, the stochastic component is the ones that make it interesting, right? That will drives the portfolio value, will make the portfolio value not deterministic, will make it random. Anyway, from our point of view, right, this is an integral with respect to the Brownian motion, right? So this guy right here is what we refer to as the stochastic integral. It's interesting, or it should be highlighted, because exactly that the Brownian motion path is nowhere differentiable. Okay, so if you try to capture this guy as a sum, okay, if you try to capture this guy, let's say, so I'll just simplify it to something, right? Add with the change in Brownian motion. If you try to capture this as this, okay, where of course, again, the understanding is the interval of time is 0 to t, you divide it, right? This is S1, this is S2, right, etc. And this is like Sn, let's say. If you try to capture this quantity, you got to be very careful, because this can only be related in a probabilistic way, okay? In other words, if you have a path of Brownian motion, and if you add them up, and you push the time interval to 0, this sum won't converge, okay? This sum won't converge. It'll give you a series that always fluctuate or will not go to a limit. So defining this object, okay, giving us a stable sense for this object so we can refer to it, because after all, right, that gives us the distribution of our, let's say, portfolio value, things like that, is a goal, right? Is one goal of the stochastic integration consideration, okay? So for the purpose of this class, right, we will not go into the whole details on how to construct this, stochastic integral. We just want to mention, right, that there exists and there is, right, a way, a consistent way to define. Okay, and now let me just reduce this to, right, this, where this is some kind of stochastic, some kind of process in time. Okay, we refer to this as the integrand, right? Called the Ito integral. Okay, usually Ito is spelled with a hat like that. The point is that this is not the only way to look at this object. There are other competing point of view, but for math finance, Ito integral is the one that is most compatible, or the Ito integral is the one that arise from this point of view. Okay, so we only discuss the Ito integral. That makes sense. That makes sense out of these conversions, okay? That allows, that kind of, makes sense for the conversions of the partial sum. And by partial sum, I mean this, okay? So now, what we want to talk about, or what we can talk about in this class, is what are the properties, okay, of the Ito integral. So first and foremost, you must remember that it is a random variable for fixed t. Okay. It is inherently random because the Brownian motion is random. Okay. So again, in this context, let me clarify, right? What usually is deterministic? Things involving t, okay? Things involving t's are deterministic. Functions involving time, right? Parameters like mu, sigma square, that kind of stuff. K, right? The strike are deterministic, meaning they are constant. If you look at it again, it won't change. And functions involving, right, WT are random. All right. For example, this is what I consider, or what I say, as a deterministic integral. This is simply t squared over 2, right? Every time you look at it, it will be t squared over 2. On the other hand, let's say a very simple one like this. Okay, you know what this integral is because it's just adding the small change of the Brownian motion. So it will give you the net change of the Brownian motion, which is just WT. So the writing cannot capture it all, but you must be aware of the context. This is a Brownian motion. So each time, right, you revisit it, it will give you a different value. Okay, just like this path, right? This is one path of the Brownian motion. Just like the binomial tree, right? Each time you pick a path, next time you revisit it, it may be this path. Another time you revisit, it'll be that path, right? So the nature of the randomness comes from different time you look, different iteration, right? Different experiments give you different values, okay? So what I'm saying is, like, if you invoke the Brownian motion in your integrator, right here, then every time you integrate, you should get a different value. It's a random variable. I say this, right, because there is always a confusion among the students between constants or deterministic objects and random variable objects. For example, when you talk about something like this, all right, because t is deterministic, it comes out, and you are left with this, which of course is 0 anyway. But if you do something like this, which I hope no one does, is complete nonsense. The reason is WT, right, is random. Expectation gives you back a number. You can never have a number comparing with a random variable, okay? So again, I understand from the point of view of writing, WT looks kind of the same as T, but right, you must know what object we're looking at, what we're talking about when we denote certain things. All right. So being a random variable, okay, being a random variable, then certain operation makes sense with it, like expectation and variance. So expectation of a stochastic integral or of an Ito integral will always be zero. And this can be explained as intuitively the Brownian motion, right? The average change around any time interval is zero, meaning if you want 50% up, 50% down. So overall net change is zero. So of course, right, that's average. But if you take any particular path, it's not going to be zero, right? Only on average. If you average out all the paths, it's going to be zero, okay? The variance will grow with time roughly, or in other words, the variance is contributed from the integrand. Of course, the bigger your integrand, the more variation the whole integral will be. But the growth, right, or the contribution of the Brownian motion in terms of the variance is like time, okay? And this, again, can be understood from the intuition that the variance of the Brownian motion grows the same way as time. But do not, okay, do not take this is an intuition. Do not take this and apply something like this. And then, I don't know, somehow come up with magical formula like this. So this is probably an example of doing the wrong reasoning and getting the right result somehow. But what you say in between is incorrect, all right? The reason is there's no interaction between the operator variance and an integral like this, all right? Again, I know that like it doesn't seem like why something is wrong like this. You pass things in, etc., etc. But just pause and think, like, you don't do something like this to begin with. All right, interaction between operator and integral, right, which or sum is a delicate business. All right, so the fact that we give you this statement, which is true, okay, which is true, requires a lot of work behind the scene, or at least some work behind the scene. It's not just like some argument of passing around operator, things like that. Anyway, right, to recap, these are the two important properties that hold universally for any Ito integral, for any stochastic integral, okay? That gives you roughly the first moment and the second moment of a stochastic integral. Also pay attention, right? This is dt, as I emphasized, because if you put dws here, it's nonsense, because that will make it stochastic, all right? A variance cannot be random, all right? Also, expectation here is required, because without expectation, this guy itself can be random, all right? When I write down something like this, I do not say it's deterministic or random. I just say something that depends on time. So in principle, this can be WS itself, all right? And as we'll see, we'll consider this kind of integral soon, the integral of WS dWS, all right? So expectation is required to make it deterministic, all right? Any question here? So the last property will be enhancing what we're saying above. So what we said above is true for any kind of stochastic integral. The next one will be if, okay, the integrand is deterministic. then we can say more about the stochastic integral. Then the stochastic integral will have a normal distribution with mean 0 and variance like this. Okay. So first, let's tie this statement back to these statements. So what else? What more do we say? What is the additional thing? The additional thing is you say something has a normal distribution. Okay, this is a big deal because when you say something has some distribution, in effect you're saying you're giving all of its moments. Okay. The mean is 0, so that's consistent with what we said above. The variance is this, also consistent with what we said above, but notice we took out the expectation. Why? Because we already assumed that it's deterministic, so we don't need to take expectation here. All right. But what's more is that, again, like I said, beyond and above these two moments, all moments of normals are known. So we say much more about this. Of course, the cost, right, or the requirement is whatever you slap in here will be or has to be deterministic for that to hold true. Okay. Any question? So let's run through a bunch of examples, okay, so that you see the flavor and meaning of these things. For example, the integral of 0 to t s dws versus the integral ws dws. All right. Yeah, go for it. Take expectation of what? Of this integral? Absolutely. This, okay, this itself is random, okay? You mean here? So 0 here is the expectation of this. Oh, here. You can, but you don't need to. For example, what is the expectation of 2? Yeah. So writing this is redundant. Or what is expectation of t? T, right? Or as you see, this right here is the example in 3. This right here is the example in 3. As you see, right? No. If you drop this, that's this right here. I'll show you, okay? That's exactly what this example will show you. So first, this is the deterministic case. So it will have normal distribution with mean 0 and variance s squared ds, or it will have a normal distribution with mean 0 and variance t cubed over 3. And you see that this makes complete sense, okay? Because this is a deterministic value. On the other hand, does not have normal distribution, okay? As we'll see later on. Okay, but let's just show you something. So first of all, the expectation of this is still 0. Okay, but let's suppose that when you take the variance, And let's say you do this. All right. Then I say that that is complete nonsense. You see why? Compare with this. Exactly. All right. So, but you see here, right? There's no need because this is already deterministic, and that's it. I mean, if you want, you're welcome to do this. It's a redundant step. That's all. But if you drop, right? If you drop the deterministic requirement, then you're down to this scenario, and no, you cannot because they are very different. Something because of something like that, and also because of this. Okay, so no, these two scenarios are quite like kind of separated. Is that okay? Sure. We'll do more examples and you see. All right. So it will be like this. Okay. And it will be S ds. And guess what? Oh, so it's fine, right? So it will be S squared over 2. Oh, sorry, T squared over 2. Okay. So let's look at one more. Let's look at this. All right, and you'll see why. So this is a stochastic integral with deterministic integrand. So it will have normal distribution with mean 0. And what's the variance? The variance is S ds because square root of S is S. Square, right? Square of S squared is S. Well, what is this? This is normal 0 t squared over 2. So I'm doing this example to show you that, right? This integral and this integral have the same mean right here and the same variance. But I hope you appreciate that they're very, very different integral and they're very, very different objects. Okay. So that's effectively one thing to point out, that, right, you need the expectation here because the integrand is random. And after you take expectation, you will get a value. Here you don't need to. You also get a value. These two values can happen to be the same. That doesn't say anything about those two random variables being the same, as I hope is quite obvious here, right? Here's the time, here's Brownian motion, here's Brownian motion against Brownian motion, all right? Let's look at something more. Now let's look at this. What about this? Technically speaking, you do not need to use the theory that we talked about above. Like we don't need to talk about 1, 2, 3 to handle this. Why? Because we know what this is. This is just WT. Okay. But on the other hand, let's see that the theory above is consistent here. First of all, this one is like 1 dWs. Okay. So this falls among the deterministic integrand. So by the deterministic integrand result, by part 3, it must have normal distribution with mean 0 and variance. But what is that? That is normal 0t, which is exactly what we always say about Brownian motion, right? That's the definition. So this is a consistency of result, right? And Brownian motion exactly has normal distribution. And I hope, again, this highlights the fact that deterministic integrand gives you normal distribution. Okay. Any question here? All right. So the next thing to talk about is Riemann integral, or rather, it's like the dt integral versus Ito integral, which is the dWt. So what is it? So here I want to look at two things. The first object is WSDS. And let's give it a name, all right? Let me call this x sub t. So here, right, the point of view is I want to look at this as a process in time. A process in time, where the process in time is defined as a Riemann integral, or the usual integral you learned from calculus against this. And let's look at another one, which is exactly the guy above. Okay. So I hope you see that they're different, okay? They're different exactly right here. The difference is exactly right here. Let's throw in one more. How about this? Okay. Oh, sorry, right? I should use s in here because t is, right? Be careful here, right? It may not mean much to you, but the t is the upper limit. So here, right, the integrating, right, the time should be s that runs from 0 to t. All right. If I put t in here, I can still understand what you're saying, but it's a little bit, that's bad taste. Okay. It should be s. Anyway, right, these three objects, again, right, it's like you're swapping pieces around, but they have very different meanings and they're for different objects. Okay, so let's go through the similarity maybe and the difference between them. So first of all, right, that is, it should be pointed out that xt, right, is a Riemann integral while yt and zt are stochastic or Ito integral. All right. So maybe let's pause a little bit. And maybe some of you may even question this, because motion maybe seem like a beast to you now, right? Like a monster. How can you even have this guy right here, ds, and you just take it for granted that is something like, my point is actually you have looked at this object before. Not really, okay? Not really. But meaning that this is some object that calculus 1 can make sense of. And so the point I want to address is you might feel suspicious because definitely Brown motion is not something you discuss in calculus 1. The point is this though, right? What is this? So you must make sense of everything, all right, when you're looking at, when you're in this chapter, because a lot of things are abstract. It's not drawn out like a tree or something for you to get a hold on. The point is, right, what do we mean by the Riemann integral? Well, here's time. You have a Brown motion path, right? Let's say this. So from 0 to, let's say, t, right? When we do the Riemann integral, we mean nothing but the area under the curve of, the Brown motion path. So in other words, the shaded area right here is what I mean by this or what I call succinctly, right, as t. So obviously, as time moves on, right, this will change, and we'll just report the area under the curve for the prime motion. Of course, it can go down, right? In that sense, you subtract the area. But one thing you may or may not remember is the area under the curve is always well defined for any path that is continuous. Okay, as long as you don't jump around too many times, then the notion of the area in the curve makes perfect sense. Now, can you calculate it? I don't think so, right? Because this path is really, really weird. Like, you cannot give our number for it. But does it make sense conceptually? Perfectly, all right? So this is what is meant by that object, okay? Like, chop it up into rectangles, add them up, that kind of thing. You get it, all right? It's these objects that you cannot chop up into rectangles and add things up because of the change in the prime motion, okay? The change in the prime motion. So if you want to appreciate it, all right, this is prime motion times the change in time. Time changes in a very regular way, right? The next second from the previous second is always 1 second change. Prime motion changes in a very irregular way, right? From the 1 second to the next, it changes, can be 10, can be -1, can be -3, etc. Right? ds is always 1, if you will, always move up. Okay. So for that matter, right, this may surprise you, but xt is differentiable in t. It's a very smooth path. All right. I don't even need the exclamation there, but maybe from this point of view, maybe let's put there to catch your attention. On the other hand, yt and zt should still be nowhere differential in t. Okay. So what I mean is this, that if you draw a graph of xt, all right, you will see, what do I want to say it? How do I want to say it? You will see a smooth path. But the smooth path is not something I can draw either. But the path is something like that. All right, it's a smooth path. Okay, but don't visualize it as something like this, because in our mind, when we think of a smooth path, we think of like having second derivative and that kind of thing all the way, right? It has concavity. Okay, this path has concavity. The xt does not have second derivative, all right, because the second derivative is a derivative of prime motion. It doesn't have it. So in some sense, xt has no concavity. Okay, however you want to try to visualize that. But if you draw the path of xt is smooth, okay, meaning no corner anywhere. While if you try to draw the path of yt and zt, it looks vaguely like the path of the prime motion. In other words, it will be jagged. Okay. Now, again, why? Why is exactly these guys are the reason why again. This is integrating against prime motion. So it inherits, right? Its change will be directly related to the change of the prime motion. Now, if the prime motion has rough change, it will have rough change, okay? And as you see soon, we captured by this idea, dyt is wt dwt. And here dzt is t dwt, all right? Why? Well, because right here, exactly, actually these two pieces have the same meaning. We'll explain that soon. But basically here it says that the change in the y is the value of the prime motion at that time times the change in prime motion. The change of z at a moment in time is a value of time at that moment times the change in Brownian motion. All right. And because this guy is rough, the roughness transfers here. Here, the change in this xt is wt dt. So sure, the Brownian motion is weird, but when you look at the change comes from here, does not come from here. So the dt, right, time change in a smooth way, so this change in a smooth way. In fact, right, exactly if you recall from the fundamental theorem of calculus, xt is differentiable any Riemann integral with its continuous integrand is differentiable, and its derivative is equal to the value of the integrand at that moment, which is wt. That's why I say it's differentiable in t, exactly coming from the fundamental theorem of calculus. All right. But of course, you see, if you try to push this to a second derivative, then you can't, because Brownian motion is not differentiable. Therefore, right, I say this graph right here should not have any concavity. All right. Any question? Let's talk about so that's some difference. But what's another level of difference? Another level difference is in terms of expectation and variance. Okay. So for this, let me change it to a little bit another x. You'll see why soon. Let's say x tilde t is EWS ds. All right. And then yt is still ws dws. And maybe let me change this to z tilde. Oh no, z is fine. I think I use s, right? All right, so we mentioned the fact that expectation of y and expectation of z, right, is 0. Okay, why? Because it's integrating against the Brownian motion. And Brownian motion on average has changed 0. Okay, half up, half down. What about this guy? Well, first of all, right, is x tilde random or deterministic? Okay, because if it's deterministic, then asking expectation for it is okay, but it's useless because it's already what it is. Well, I hope you see that it's not deterministic because of the Brownian motion aspect here, right? You have the Brownian motion in your integrand, automatically that makes it random, right? So you're adding, right? Basically, you're adding the area under the curve of some Brownian motion path. Of course, right? So this is one particular path, which gives rise to this area. Another time, right, you get this path, which gives rise to a different area calculation, okay? So that's why even though it's a dt integral, it's still random, okay? And if it's random, then it's worth our while to ask about expectation and variance. So expectation will be expectation of this. What do you do here? All right. What you do here is a semi-mysterious result that says that you can exchange expectation and integration. Okay. So I passed the expectation inside. That's valid. That's valid if the integrator is ds, okay, is dt. This is not valid if it's dwt, okay? I'll emphasize again. But here it's valid here, and what you get is e to the 1/2 s ds. All right, and whatever that is, I'll let you calculate out. But the point is, right, it's non-zero. Or I mean, I think I can calculate out for you here, right? It's going to be 2 e to 1/2 t minus 1, which is non-zero. Okay. So the point is, right, an integral, a dt integral, even if, right, that the integrand is stochastic, right, its expectation does not have to be 0. Again, why? Because time marches on, right? Time marches on, time goes up. So it's like, you know, you have a, roughly speaking, some kind of return with stochastic rate. That doesn't mean that overall you should get 0 return, right? Unless your rate on average is 0, like xt. Like that's why I changed to x tilde t, because xt kind of hide the picture a little bit. If it's this, okay, then I can exchange expectation and integration, and Brownian motion has expectation 0, so I get 0. But that's why I don't want to give this example right away. The reason is you may confuse this with this guy. Okay? The point is, this is always 0 because of dw. This is 0 in particular because of this guy. If I change it to something else that's non-zero mean, then I'll get a non-zero result at the end. Any question here? So the highlight is the interchanging, okay, between expectation and integration. And by the way, all right, this is not so strange. This is like when you take expectation of a sum. I hope that you have seen this as a natural result, that expectation of a sum is a sum expectation. This is linearity of expectation. So an integral, okay, in some sense, is like a continuous sum. It's a sum when you push the, you know, there's a d delta t here, goes to 0. And so in some way, exactly by linearity of expectation, you can exchange, okay? That's the reason. Of course, I'm hiding every a few conditions, okay, under the rug. But roughly speaking, you can exchange expectation and integration against dt in this class. That's fine. But so caution, okay? And here's one difference. Again, I know that many things look so familiar, so similar right now that you know, you don't know what is what. This is not this. All right. Do you see why? Because this right here is still random. All right. And this is an expectation, so I cannot have an expectation equal to a random variable. Plus, you cannot exchange expectation and integration when the integration is stochastic integral. All right, that's not allowed. The exchange is when the integration is with respect to dt. So that's not true. And by the way, right, the answer here is just equal to 0 by the general result of the stochastic integration that we talked about. Okay, it should be equal to 0 only. All right. Second remark is this, also among the caution line. The variance, let's say, of this will be, suppose you do this too. Or you do this, either way. Both of them are questionable, or actually both of them are wrong. Okay. So here is another attempt of the students applying a result where they don't belong. Remember the result we talked about, right, above? Is for stochastic integral. So it must be a DWS before you can apply that result. The DS here does not allow that, all right? So this is not true. Why? Because the variance of a sum, right, does not equal to the sum of the variance in general, okay? Well, why? Because I know many of you will do that on instinct, but that's not true if these guys are not independent. So exactly, right, when you add a bunch of exponential of the Brownian motion, there's no reason why they're independent. They're actually dependent. So that's why the first attempt failed. The second one is trying to apply this kind of thinking. And again, I hope you see that that's false. The sum of the square, sorry, the square of the sum, that's what you're trying to think, is somehow the sum of the square. That's also false. Okay. So results, right, must be applied to their appropriate context. And the two main contexts are the DWT and the DT terms. We will have to discuss both. All right. Why? Because the typical stock model, okay, the typical stock model, whoops, where was it? Let me rewrite that. Doesn't matter. We have to discuss both because a typical stock model, the Black-Scholes model, is that you have DST, all right, or let's just say the log return. D log ST is mu dt plus sigma dWt. So inherently in the return structure of any stock has a time component and has a Brownian motion component. So we need to deal with both. And the time component will easily get mixed up with stochastic component. For example, right, dst is mu st dt plus sigma st dWt. All right, both of these are Black-Scholes. Again, right, could be super confusing to you. What is this? This is the log return. This is a model for the log return. So the log return has average return rate mu and standard deviation sigma. This actually is a model for the change in the stock price only, right? It does not have a return notation meaning. Or if you want, here's the return. This is the return. So this model is the percentage return. I just divide ST here on both sides. Okay, so this is the model for percentage return. But you see, viewed in this way, it says that the change in your stock price, which directly related to your portfolio, right, net gain, net loss, will be some stock, right? The time component has the stock price in it. And stock price, because it inherently depends on the Brownian motion, right? The discussion of something like this will not be, too much out of place. It will be very, very common to show up. All right. So keeping your head straight against about the T and the DWT integral, okay, is crucial to do the right thing in this context. Any question? All right. So now let's move on to the second. So that was basically some aspects, okay, of stochastic integral and some, the Riemann integral as well, like basic properties. Okay, so I was introducing the object to you. The object being, this guy, and right, his cousin, these guys. Okay, and the properties and how to work with them. They're stochastic properties. Now, just like good old calculus, all right. If you remember in Calc 1, all right, you start to learn something about this kind of thing. And then you say, well, I can give it a name. It's a function. And I can do, right, something like g prime of t, which is ft, all right? Or, if you want, right, dg over dt is like this. And you can play with, the chain rule. I don't know. Let's say you put, let's not make it too exotic, right? Let's do t squared. Meaning you change the limit here a little bit, and then you wonder, how does this change? And so it becomes the function evaluated, right, at that point. So t squared times the derivative of this one, right, times 2t dt, that kind of thing. So my point being is that, so this is correct, okay? My point being is that from calculus 1, right, you learn about the integral, and you learn how to play around with the integral with differentiation rule, okay, which is the reverse aspect of the integral. So that's how you should view this kind of operators. Integration and differentiation are sort of like two opposite directions, okay, of the same process, which is whatever, like analyzing the function. So here, right? Oh, and by the way, right? So the main result is something like this. One of the fundamental result in Calc 1, by the way, right? And actually, I'm quoting the fundamental theorem calculus here for you, that if you have a function, okay, if f of t is differentiable in time, then it can be represented as an integral. Okay. So again, let me just spell this out in English. It says that f of t can be represented as a Riemann integral. All right. So basically the fundamental theorem calculus, right, just say something quite simple in English. It says being differentiable, and being represented as a Riemann integral is one and the same thing. All right, and I understand, right? When you took Calc 1, you're like, so what, right? Why make life so complicated? I have a function, right? I can just deal with it. Why in the world do you want me to like look at it as an integral? That just makes it way more problematic. The answer is no, right? We invent things to make things easier for us, not harder. First of all, there are many things that you cannot represent it. You cannot represent as an explicit function. Okay? One of the fundamental illusion of a Calc 1 student is everything can be represented explicitly. All right? While in real life, many objects of interest to you cannot be represented explicitly. For example, this guy right here. Okay? What does it represent? It represents, right, you know what I'm talking about. This represents the probability of a standard normal is below t. But obviously, right, you cannot represent it as a function of t explicitly. This does not have an explicit antiderivative. Okay? But of course, right, I hope by now you're very comfortable with, seeing this as a function in time. But a Calc 1 student, I think, may have some, I don't know, anxiety about seeing this as just a function of time. Okay? But that's one thing. And another, of course, it says that if this function is differentiable in t, great. I'll just relate it back to its derivative. All right. But the point of view that representing a function as a integral is an enrichment, okay, of the way we discuss math, not a complication. So the same thing here happening in right now for us, that now we have, right, for us, we have, right, the stochastic integral. So immediately, similar question happens that can we, right, we want to discuss about the ways to relate a function, okay, like this. The function in time and in Brownian motion to a Riemann integral plus an Ito integral. All right. So I hope that, so okay. So let me give you an example of what this statement means. This statement means something like this. Wt squared, for example, will be the integral from 0 to t, ws dws. Hold on, give me a second, okay? 2ws dws plus the integral from 0 to t of ds. Yeah, all right, something like that. So this is what we have in mind. So right here, Wt squared is what I mean by the function Twt, right? This is the Riemann integral. This is the stochastic integral. Okay. Something else? Well, Twt will be the integral of s dws plus the integral of ws ds. Okay. So another example. So yeah, okay. So again, right, the the philosophy is very much in this kind of um, flavor. That is, you have a function and you want to express it, right? But now, of course, because the function itself um, involves the Brownian motion, so a Riemann integral alone is not enough. Okay, a Riemann integral alone is not enough, because if you can express something involving Brownian motion using Riemann integral alone, then you imply that this guy is differentiable, because the Riemann integral is differentiable in time, which obviously is not true if you have a Brownian motion component here. So you need the Brownian motion component. On the other hand, using the Brownian motion component alone is not enough, as we'll see. All right, you need the Riemann component as well. So both. And I think, right, the example, the prime example, right, that we have about a stock price model or Black-Scholes model is that, right, if you have ST, right, which is S0 e to the, let's say, mu t plus sigma dwt, all right, then it can be expressed. So basically, right, only this guy right here as S0 times the integral of S sub u, okay? Give me a moment here. There's some complication, so let me write it. I want this minus 1/2 sigma square, like this. Then it will be this mu dwu plus, sorry, this is du. Like that. Okay. So the stock price itself is also a sum, okay, a sum of a Riemann integral and a stochastic integral. And you're like, yeah, but that's a little weird, right? Because SU is in here. Well, never mind that, because SU has an expression. So, oh, sorry, right? There's no S0 outside here, just SU, like this. So SU right here has an expression. And the point is, if you plug this complicated expression in here, you will get the right result. Okay, you will get this. It's almost like the flavor of it's like this, e to a t, right? I think by now you are not surprised to see that one. So sorry, here's S0 plus 1 plus the integral e to a u du. Right? You're not surprised by this result. But of course, you see e to u is being the function also comes in here. And the ultimate answer is that because differentiating e to t, you get e to t, right? But so the stock price itself, right, again, is susceptible to this representation. In fact, this representation is what allows us to solve a stock price model like that. Okay. So anyway, all of this process, right, will be the focus of the next chapter or so, the next lecture or so, and it falls under the answer, the topic of so-called Ito formula. Okay. Any questions so far? So first, let me lay out the context of Ito formula, all right? The Ito formula will give you something like this. The Ito formula will give you, right, that the ultimate, the most, the most general formula will be like this. dftwt is f sub t dt plus f sub x dwt plus 1/2 f sub xx dt. All right. So actually, this is not most general yet. There's another formula that's more general than that. We'll talk about that soon. But basically, I just want to kind of make sense out of this. So the generic structure you'll see is like this. D of something involving, okay, T in prime motion will be something dt plus something dwt. Now, we may or may not just spell out everything like that, like there's two dt terms here. There's a reason why we do it that way. But you could combine them into one dt term. In other words, you can combine them into ft plus 1/2 fxx dt plus fx dwt. Okay. But the point is that what does this mean? Okay, what does this mean? Because as I advertised above, right, the goal is to break a function into a Riemann integral and an Ito integral. But I'm writing something like d here, right? What's going on? The answer is that the Ito formula is usually presented this way. Basically, I want to say this is a differential form, okay, of the Ito formula. How do you transform a differential into an integral? Well, it's easy. Basically, remember that for any function, okay, any process, if you integrate it, sorry, what am I saying? If you add up a small change over time, then you will get it is net change. All right. So if the generic structure is given like this, right, like the above, for example, then what happens is you can integrate both sides. Let's say this, right? That's this guy. I do realize that I'm mixing notation here. This doesn't mean f evaluate at t. This is the partial of f with respect to t. So let me do this. Okay. I think this is clear. This is a partial with respect to x of f. This is the partial, second partial. All right. So what we mean is, all right, that there will be partial t of f plus 1/2 the second partial of f with respect to x. This whole thing integrate with respect to ds. And then we have the second, also the first derivative of f with respect to x integrate with the Brownian motion. Okay. On the other hand, what is this guy right here? By this result, right, this is just the change. So this is that. Hold on, let me separate this, right? So what I want to say is the differential form of the Ito integral of the Ito formula is equivalent to the integral form if you integrate the differential. And remember that if you integrate the small change, you get the net change. All right. So our goal, right, for our next class is to go through different version, all right, of the Ito formula right here, taking the most simplest function of f, the simplest function of f, like this, all right, the simplest function possible, like this, and then build it up to a more complicated structure, like this, all right, all kind of under this kind of umbrella, okay? And in some way, if you want, we are differentiating with respect to the Brownian motion, all right? Any question? Okay, if not, then I'll see you on Friday. You too.